Hi everybody, I'm going to do a recording of the main topics from 9.1 and 9.2 for you. I'm not a super happy camper because I just did the whole recording, but without the audio going, so I'm starting over. So, looking at chapter 9.1, we are starting to think about how we might compare two population means. So up until now, everything we've done in 8.1, or in chapter 8, was thinking about how we might do, we had that case 1, case 2, case 3 business. And in all of those, we were thinking about comparing one population's mean with a number. So we're wanting to know, is the true population mean equal to some particular null value? So comparing mu to the null value mu naught. So that's all we're doing, is thinking about a individual population's population mean, or sometimes we're also thinking about comparing a population proportion to some particular population null value. So we had that kind of division between are we talking about mu or are we talking about the population proportion P? And when we're talking about mu, we have case 1, case 2, and case 3. And we talked about hypothesis tests and confidence intervals for both. In chapter 9, we're going to have a similar kind of taxonomy of how we arrange these problems. We have a case 1, case 2, and case 3 still, except for we're talking about the difference between two population means. So for right now, leaving aside thinking about population proportions, let's just think about population means. We can think about how we might compare two population means, and we're going to call them mu1 and mu2. So let's look at this example problem. Here we have two populations that we're thinking about. Population 1, population 2. Okay, the first population is going to be heat-treated steel specimens. Okay, and the second one is going to be cold-rolled specimens. So those are the populations, and each population has its own mean, which would be the average hardness, the true average hardness for these specimens. So mean in the first population, I'm going to call mu1, and the standard deviation in the first population, I'm going to call sigma 1. And then in population 2, you can guess it's going to be mu2, and the standard deviation is going to be sigma 2. These are the unknown population quantities, okay, that have these that are called these letters. So the parameter of interest in these kinds of problems, if you'll recall, we had a parameter of interest in the one population scenarios from chapter 8. The parameter of interest here is going to be mu1 minus mu2. That is the bit of information that we're after with our hypothesis tests or our confidence intervals. We'd like to be able to actually think about mu1 minus mu2 as its own quantity that we are interested in learning more about. So the way we're going to end up writing our hypothesis tests is we will have a null hypothesis and an alternative hypothesis still, but they will both be based on this difference, mu1 minus mu2. And maybe we have them equal to 3 or greater than 3. I'm just using 3 as an example. This is what you guys will recall we called it looks like what we were calling the null value before. It's the same idea. It's what the parameter of interest is equal to in the null hypothesis. Most of the time for these problems where we have two populations, our null value is actually going to be hold on a second. Our null value is going to be 0. So you'll find in most of the problems that we're doing, we're interested in knowing, is mu1 minus mu2 equal to 0, or is it not equal to 0? And that makes sense because asking, if you think about the null hypothesis here, mu1 minus mu2 equals 0, that's the same thing as setting mu1 equal to mu2. If I just move the mu2 over to the other side. So when we use a null value of 0, that allows us to ask an important question, which is, excuse me, is mu1 the same as mu2, or is it different? All right, so for the next slide, I want to clarify this heading here. It's really two independent samples from two populations, because later on we're going to get to a situation where we are not, where our samples are not independent of each other. They are related to each other in some way. However, right now, for everything we're doing today, we're thinking about two independent samples, meaning they have nothing to do with each other. If you can't like pick an individual from one of the samples and say, oh, that they're related to somebody in one of the other samples in some kind of systematic way. We don't have that happening. So the sample notation that we're going to see for when we actually draw these samples, well, we have sample 1, and we have sample 2. Sample 1, just as a quick reminder, sometimes we use this phrase IID, which means independent and identically distributed. So sample 1, every observation is an independent and identically distributed random draw from a random variable that represents the population. Okay? So we think of sample 1 as IID random draws from the random variable x. And the sample mean we're going to write as x bar. The sample standard deviation we're going to write as S1. You could also write it as S with an X in the subscript, which maybe would make more sense in some ways, but I'm following how the book does it. And then sample 1 we're going to say has a sample size of m. And then we're going to say that the standard error of x bar, meaning if you think of the sample mean as a random variable itself, because it's drawn from this population, repeated draws from the same population, the standard error of x bar we're going to write as S1 over the square root of m. And that's based on what we know is true about the distribution of the sample mean, just generally. Sample 2, the notation is going to look like this. Y bar is the sample mean. We have S sub 2 for the sample standard deviation. We've got n for the sample size, and then the standard error of y bar is S2 over the square root of n. So what we're interested in here is how to estimate mu1 minus mu2. Because mu1 minus mu2 is really what we're after. We're after knowing, are these guys, is this difference equal to 0 or is it equal to something else? So we're going to use, to do that, the obvious thing would be to use the difference in the sample means. So think of each of these sample means as its own kind of random variable because it's drawn from the sample. Then we know some things about the difference in sample means. We know the expected value of the difference in sample means. And that's because, if you'll recall, you can kind of distribute the expected value to get this. And the expected value of the sample mean of the x's is just going to be the same thing as the expected value of any draw from x. And we said on the previous page, the expected value of x is mu1 and then minus mu2. So we know this about the expected value of this difference of sample means. We also know that the variance of x bar minus y bar is going to be the variance of x bar plus the variance of y bar. And we know that because, remember, you have to square the coefficient of each random variables when we're thinking about a variance of a linear combination. These guys are independent of each other, which is why we can even do this. But then we have to square their coefficients, which is what causes us to get a plus here instead of a minus. And this, according to what we know about the variance of the the variance of sample means, is going to be sigma 1 squared over m plus sigma 2 squared over n. Okay, so that's what we know so far about this quantity x bar minus y bar. And so, based on that, we can start to formulate a test statistic because we kind of know how x bar minus y bar should behave, assuming that we know how x bar minus y bar should behave based on what we know its mean and variance are. So I'm going to start, it says 2 scenarios here. We're used to thinking about 3 cases. I'm just thinking about the first 2 cases here. So we have our 2 cases that I'm thinking about are case 1 and case 2. These are directly analogous to case 1 and case 2 in the one population scenario. Directly analogous. Just means that when we were talking about one population, the first case, so case 1, was when we had a normal population with known population standard deviation. So here we have normal populations with an S, 2 normal populations, and then known sigma 1 and sigma 2. So we know both population standard deviations in this scenario. So that totally makes sense. We have case 2, and recall when we had one population, we were saying, okay, in case 2, we just have to have a large sample size. Here, similarly, we need large samples for both. And we're going to require m and n to be both greater than about 40. 30 to 40 is kind of the magic number for what it means to be a large sample. Here for these, I'm using 40, but I don't want you guys to get hung up on what constitutes a large sample at all. If you're in the 30 to 40 range, it's fine, and I'm never going to give you a question on a test or a quiz that is nebulous. So it's always going to be just a very small sample, like 8, or it's going to be like 70. So I'm going to make it clear to you guys whether it's a large sample on questions I might ask you. Okay, so so it says known population standard deviation. So that is case 1. The other thing that we require in case 1 is that we have the normal populations. And so that's an assumption here for this test. But this is the description of how the test works. And you can see that it looks very similar to how the test worked when we had one population we were working with. Except for here, we have this thing called delta naught. Okay? And that is the null value. So let me write this down. The null value. And so just recall, for one population, we had that the null hypothesis looked like mu1 equals sorry, not mu1, just mu equals mu naught. So we had that null value that had the 0 in the subscript, and we were saying our excuse me, we were saying our parameter of interest was mu, and we were setting mu equal to mu, the null value in the null hypothesis. Here we're doing the same thing. We're just calling the null value delta naught, and again, usually for our purposes in this course, we're going to let delta naught just be 0. So then we have what the test statistic looks like. It should have a z distribution under the null hypothesis. So that means when we calculate our p-values, we're looking to see if the null is true, then that means that my test statistic should have a standard normal distribution, and we have to see how unusual it is in the world of the standard normal distribution. So let's see a problem with this. Analysis of a random sample containing M equals 20 specimens of cold rolled steel. Okay, so we have 20 cold rolled steel. Already I can see I've got something that's going to be useful to me, and that's the sample size of the first sample, or the first population has a sample drawn from it of sample size 20. We have, this is 20 specimens of cold rolled steel to determine yield strengths. So the sample average strength was this X bar here. Then we had another sample, and this is not from cold rolled steel, but two-sided galvanized steel. So that's what makes this population different. And its sample average strength was Y bar. Assuming that the two yield strength distributions are normal. Okay, so we have that assumption that we need. And we are told the population standard deviations. The fact that this problem writes them with sigma instead of S tells us these are population standard deviations. So that's what we need to do this problem. The question that is actually being asked here is, does the data indicate that the corresponding true average yield strengths, mu1 and mu2, are different? We want to know. So mu1 minus mu2 is the parameter of interest, and we want to know, are they different? Does mu1 equal mu2? Well, mu1 equaling mu2 is the same thing as mu1 minus mu2 equals 0. So that is our null hypothesis. The alternative is that they don't equal each other, that mu1 does not equal mu2, but that's not how I write it. Let me just back this up. I want mu1 minus mu2 to not equal 0. That's what I'm after here. So, just as a quick reminder, this thing right here, that's the null value delta naught, which technically could be different from 0. And we could use this test procedure for something different, for a null value that's different from 0, if we were interested in knowing something other than does mu1 equal mu2. If we wanted to know, is mu1 bigger than mu2 by 3, then we would use 3. Does mu1 exceed mu2 by 10? We would use 10. Is mu2 larger than mu1 by 3? Then we would use negative 3 for our null value. But usually we're going to be using 0. Okay, the formula for the computed value of the test statistic. Z equals, this is just taking it from the previous page. So I'm just copying it over. Now we have to actually plug into the formula. Z equals, all right, we have 29.8 for X bar. We have 34.7 for Y bar. We have 0 for the null value. We have 4.0 squared over 20 for that first part of the denominator, and then 5.0 squared over 25. And when you do the arithmetic here, you get minus 3.66. Okay, so this is a Z test, meaning we're going to go to the Z table to see if our computed test statistic looks extreme. So you can do that in a couple of ways. You can go back to the table here, and you can see, okay, my null hypothesis had a does not equal 2 in it, so I'm going to use this. 2 times the area under the standard normal to the right of the absolute value of Z. So you can absolutely use this, and if you are kind of uncomfortable on the intuition of what we're doing here, when I talk about testing for how extreme our test statistic is, you can just use this, okay? That's all you have to do, is literally do this calculation. So I'll do that with you guys right now. 2 times the area under the standard normal curve to the right of Z bar. So Z bar is going to be 3.66. The area to the right of Z bar equals the area to the right of 3.66. But remember, the standard normal table only gives us areas to the left. So this is 1 minus the area to the left of 3.66, which is 1 minus whatever I look up in the table for 3.66. So if you go to the standard normal table and 3.66 isn't even on there, it's like beyond, I think the table only goes up through 3.5. And at that point, you're getting values very, very close to 1. So basically, you're doing 1 minus 1, which is 0. And I'm going to put it out to a few decimal places here. So that's what you get for the area to the right of z bar. And actually, we're trying to calculate 2 times that. So we want 2 times 0.000, still 0.000. So that's our p-value, which we got just by following the instructions there. So as you don't have to have any kind of intuition on what we're actually looking for to do it that way. I will say, I think it's helpful to think about it intuitively, and sometimes it leads you to not having to do quite as much arithmetic. Not that there was much arithmetic involved here, but the idea here is you've gotten this value for your test statistic, and you have to think to yourself, is that extreme given that the null hypothesis is true? And what I mean by that is, if the null hypothesis is true, then this whole quantity, this whole z, should be standard normal. So you could say, okay, I know that I expect this z to look like this it's a random quantity, it's based on the sample. So I expect that it's going to look like a standard normal distribution. And I got something that was minus 3.66. It was way out here in the tail. So the minus 3.66 is here at this x value, at this value on the x-axis. But the question that you must ask yourself now is, how weird is it that I got that? How unusual is it? And so you do that by finding out the probability of getting something like 3.66, I meant to write, or more extreme. So you have to include all the probabilities from minus 3.66 all the way out to why it keeps going away? My 6 keeps, I don't know why that keeps happening, guys, but I'm trying to make this into a 6, and it just keeps going away. 3.66, okay. So the idea here is you're trying to find out the probability of getting that minus 3.66 or anything else similarly extreme, and you have to recognize that when we're talking about extreme values in the direction of the alternative hypothesis here is saying this is when the true population mean is, the difference in true population means does not equal 0. So we're expecting this difference in sample means, x bar minus y bar, when I subtract off its mean and divide by its standard error. I'm expecting that this z is going to be standard normal, and it's going to be centered there around 0, and so extreme values would also be from here on out, 3.66 and above. So the way you could do that is, if you know this is what you're looking for, these probabilities in the tails, then you could just look up minus 3.66 in the table, since the table gives you negative values, and recognizing that the standard normal table is symmetric, then you just multiply by 2. So in this case, the probability that a standard normal random variable is less than minus 3.66 is like 0. You're going to get like 0, 0, 0, 0 in the table, and you multiply it by 2 again, and you get still zeros. So we're on step 7 now. Compare the selected significance level to the p-value. So our significance level was 0.01. Our p-value was 0.0000, which is less than significance level alpha. Therefore, we reject H naught. Now let me write this in here. We do have evidence. We do have evidence that the average yield strengths differ. Okay, that's what we have evidence of. We have evidence in favor of the alternative hypothesis that mu1 does not equal mu2. That is, mu1 minus mu2 does not equal 0. Okay, so this was everything. This whole test was set up for case 1, where we know the population standard deviations for both populations. Case 2, just like in the one population situation, case 2 is where we have a large sample, where both populations, we have like 40 or more in both populations. So we compute this in the exact same way that we did the previous test. It's exactly like the known sigma test, or known sigma 1, sigma 2 test, I should say. In this case, however, normality is not required, and that is due to the central limit theorem. And then we're gonna carry out the test in the exact same way, except for we're gonna use S1 and S2 in place of sigma 1 and sigma 2. So just like we did in the one population situation, we're doing the exact same thing. We're just going to do the test in the same way, but we're going to recognize that we're using the sample quantities for standard deviation instead of the population quantities. And that's fine because we have a large sample size, and therefore our sample quantities are going to be excellent estimates of the population quantities. So that makes this not complicated. All we have to do now is carry it out in the exact same way. So I'm not even going to do an example of that one. The last thing I want to show you for this section is that we have confidence intervals which correspond to the two hypothesis tests that we've already done. So basically, if you take the quantities in those hypothesis tests and you kind of rearrange them, you're going to end up with these two confidence intervals. And in both of them, we have an estimate for mu1 minus mu2. That's what both of them have right there, the x bar minus y bar. And then in both of them, we have this part here, which is the standard error of our estimate. The standard error of x bar minus y bar. That's what both of those are. One is the true standard error because we know the population standard deviation. The other one is an estimated standard error. We just still call it the standard error. So that's how confidence intervals usually are structured: an estimate, and then we have some kind of multiplier based on the null distribution, and then we have a standard error or its estimate at the end. So this one is a case 1. This is a case 2. And those should all feel very easy. They'll be very similar to doing it as we did it in case 1 and did confidence intervals for case 1 and case 2 in the one population situation. Okay, that's it on